So you consider this figure. A dash, B dash, C dash. Here 8.5 meters. Here 8.5 meters. The interspacing is 80 centimeters. So we have to now calculate the inductance per kilometer and also per phase. How you calculate what is the inductance? 0.2 natural logarithm of GMD by bundled you write self GMD, but numerator is mutual GMD, millihenries per kilometer. So what is self GMD, mutual GMD here? Eight point five, 17, apply cube root. Now, how to find what is self GMD? You can find for any phase, or you can find for any subconductor A. How to find for a subconductor A? Check in the question. Each phase conductor has two subconductors. The subconductors are symmetrically spaced. What about A now? Its radius R dash, A dash. Two distances we apply square root. Now further you are given this point in the question. Diameter is 5 centimeters. What about dia? 5 centimeters. So radius 2.5. A dash is 80. So now you apply square root. Find out what is the self GMD. Now find out what is the inductance per phase here. You substitute the values here and evaluate. You get what is the inductance now in millihenries per kilometer. So this is the part of calculation required in this question. Now we solve this next question based on the capacitance calculations. What is the capacitance of neutral per kilometer? Of a single phase line composed of conductor with radius 0.328 centimeters spaced 3 meters apart. So with respect to neutral means CAN. How to find 2 pi epsilon naught epsilon r by natural logarithm of d by r, so many farads per meter. Substitute the values. Epsilon naught 8.854 10 power minus 12. What is the distance now? 3 meters. Radius 0.328 centimeters. So on simplifying this one, 0.00817 microfarads per kilometer. How much you get? 0.00817 microfarads per kilometer. So the transmission line is operating at 50 Hz and the conductor is arranged as shown. So next we say that it is operating at 32 kV. The radius of each conductor is 1.5 centimeters. The capacitance per kilometer is. So in the figure you are given these distances 1.6 meters each, here 3.2 meters. First to find out GMD here, 1.6, 3.2, 1.6 cube root. You get 2.61 meters. What is capacitance per kilometer is what we have to calculate. Now you are dealing with the three-phase system. For three-phase system, you calculate the capacitance per phase. So you are dealing with the three-phase system, calculate the capacitance per phase. So how to find the capacitance per phase? It is similar to the capacitance with respect to neutral, like in the last case. So use this one. Use this formula and accordingly find out the answer. Epsilon naught how much? 8.854 10 power minus 12 into 1. What about GMD now? 2.61. What about the radius? 1.5 centimeters. So find out the capacitance per phase. 11.5 10 power minus 9 farads per kilometer. Now we solve this next one. A two-conductor single phase line operate at 50 Hz. The diameter of each conductor is 4 centimeters and are spaced 6 meters apart. The capacitive susceptance to the neutral per kilometer is. Capacitive susceptance to neutral per kilometer is. So that is what we have to calculate here. So neutral means, again you find out CAN. What is formula to find CAN? 2 pi epsilon naught epsilon r by natural logarithm of d by r farads per meter. Epsilon naught is 8.854 10 power minus 12. What is the spacing now? 6 meters. R how much? 4 centimeters. Calculate, you find what is the capacitance here. So you get 9.75 10 power minus 12 farads per meter. Capacitive susceptance means BCN. Outright omega CAN. Omega is 2 pi f. CAN 9.75 into 10 power minus 12. So 3.06 into 10 power minus 6. So minus 9 Siemens per kilometer. So minus 9 Siemens per kilometer. So this is how you represent and find the capacitive reactance, capacitive susceptance here. Now we solve this next question. What is the capacitance per kilometer per phase? The diameter of each subconductor is 3 centimeters. Now, you have to find out the capacitance per phase per kilometer. Now, what is the formula to calculate per phase means 2 pi epsilon naught epsilon r by natural logarithm of d. You write it as GMD. You are dealing with bundled conductors. You write it as GMD. Which GMD? Mutual GMD by R is there. Okay, though R is there, but you write the formula as self GMD. Capacitance calculation independent of GMR, independent of GMD. But initially you write as self GMD so that you can substitute the values without any difficulty. So what is the mutual GMD? 6.5, 6.5, 13. You have 3 distances, apply cube root. How much? 8.18 meters. What about the self GMD now? It is same as for any one phase. And it is same as for any one subconductor. It is same as any one subconductor. And what about the diameter? 3. You write 3 by 2. And what is the distance from A dash? Include the distance. A dash. 2 distances, you apply square root. How much? 40 centimeters. So under root of 60, 7.74 centimeters. So now you substitute 2 pi 8.854 10 power minus 12 epsilon r is 1. What about mutual GMD? 8.18. Self GMD 7.74 10 power minus 2. So calculate and find out 0.1198 microfarads per kilometer. But observe important point, you are not writing R dash here. Check this important point. At this point you are not writing R dash, it is only R. Because for capacitance, there is no significance of radius. Because charge is deposited only on the surface of conductor. So only that part calculation is important where you write it as R. So this is regarding the calculation of capacitance. Now we come across the next topic, overhead line insulators. Now the next topic is overhead line insulators. So what is the function of overhead line insulators? They provide electrical isolation between current carrying components and other conducting elements. And how these overhead lines insulators are classified? They are classified based on, first one is as per construction. So first we will check as per the construction. As per the construction details, you have two classifications. What you call this one as? This one as a lattice tower structure. This is a lattice steel tower structure. And other structure you have like this. So where you come across R, Y, B. And here you come across cross arm. Now what is the function of cross arm? The function of cross arm is to provide uniform line to line distance. What is the function of cross arm? The function of cross arm is to provide uniform line to line distance. Is to provide the uniform line to line distance. Now we check the properties of insulators. Properties, first one is the high dielectric strength. How you express kV per centimeter per peak. Now we are checking the properties of insulators. So the first property of insulator is high dielectric strength. Second one is, what about the thickness of insulator? So for a given operating voltage, do you prefer insulator with less thickness or high thickness? You prefer an insulator with less thickness. So for a given operating voltage, an insulator should have less thickness. And what about the leakage current or the leakage resistance? Leakage current must be low and leakage resistance must be high. So what about the leakage current? Must be low, or you say that the leakage resistance must be high. And what about the next one? An insulator should not absorb moisture. That is, an insulator must be non-hygroscopic. An insulator must be non-hygroscopic. That is, should not absorb moisture. Next one is, an insulator must be free from impurities. So how you name the free from impurities? So an insulator must be non-porous. An insulator must be non-porous. That means it should be free from impurities. And further, insulator should have high mechanical strength in order to withstand its own weight and the effect of wind. And the effect of wind. So it should have high mechanical strength. So insulator should have high mechanical strength. What for? In order to overcome its own weight and the effect of wind. So these are the properties of insulators. These are the properties of insulators. Now we check what are the materials used as insulators. We use the most commonly used material. The most commonly used material is porcelain. And what is the composition of porcelain? Composition of porcelain, it has three materials: 20% silica, 30% iron component Fe, and 50% clay. And other is 50% clay. So these are the this is the composition of porcelain. So here you name it as 30% feldspar, that is iron alloy. And what is its dielectric strength? The dielectric strength is 60 kV per centimeter per peak. What about dielectric strength? 60 kV per centimeter per peak. And also we have the dielectric strength 15 kV to 17 kV for every 1/10 inch thickness of insulation. This is porcelain data. And other one is silica, or you name it as toughened glass. So here only single material, 100% silica. And what about its dielectric strength? Double, 120 kV per centimeter per peak. This is the data regarding silica or toughened glass. Now, other than these two, we have three important points. Insulator for indoor substations are made of which material? They are made of synthetic resin, RESIN. And insulators for EHV applications and UHV applications are made of which material? Silica or toughened glass. Made of silica or toughened glass. And the insulators used in the switching substations is known as post insulator, known as post insulators. So this is regarding insulators here. So next we have the classification of insulators based on applications. So classification of insulators, secondly, is based on applications. So how to classify them based on applications? First one is distribution system. Where we have pin type insulator. And what is the operating voltage a pin type insulator can withstand? Up to 11 kV, or extended further up to 33 kV also, but basically 11 kV. This is the insulator we use for distribution system. And what about the next one? We have a shackle type insulator. So when you use this shackle type insulator for specific applications, what are those specific applications? Say the deviation of distribution line is beyond 3 degrees. We use shackle type insulators. Or you have a dead end of a distribution line. We use shackle type insulators, and not only for that, for all the railway crossings, road crossings and river crossings, we use shackle insulators. And similarly for transmission system. So what about the classification? First we have a string or suspension insulator, and other one you name it as a strain or tension insulator. Strain or tension insulators. Anyway, we discuss further string or suspension. When we use the strain or suspension insulator, similar to these applications, that is, when the deviation of transmission line is more than 3 degrees, not 33 degrees, we use strain or tension type insulators. Next one is the dead end of a transmission line. We use strain insulators. Next, for railway crossing or road crossing or river crossings, we use strain type insulators. Okay, now we check regarding string or suspension insulator. So you consider a string or suspension insulators. So what does the string or suspension type of insulator consist of? A string or a suspension type insulator consists of at least two insulators arranged one below the other. It consists of at least two insulators arranged one below the other, and it forms a string. And further you say that they form a string of insulators. So what about this string or suspension insulator? You say that they consist of at least two disc-shaped porcelain insulators, two disc-shaped porcelain insulators, and they are connected each other to form a string. And one end of the string is connected to cross arm and other end of the string is connected to power conductor. So where one end of string is connected to cross arm, and other end of the string is connected to power conductor. So represent one insulators. So here we are representing a string of insulators. So I have represented 4 insulators here. Any 2 insulators, how they are connected? By means of this metal part. By means of metal part. And each disc can withstand how much kV? They can withstand an operating voltage of how much? 11 kV. So this is how at least 2 disc-shaped porcelain insulators are connected one below the other to form a string. Now why particularly this shape is given for the insulators? You observe, this is the shape you have given to the insulators. So you can observe, you are increasing the length for the flow of leakage current. As length increases, what about the resistance? It is rho L by A. As L increases, R increases. If R increases, what about the leakage current magnitude? Decreases. So what about the leakage current magnitude? Decreases. So in order to decrease the magnitude of leakage current, this particular shape is given to the insulators. And how you check the utilization of insulators in a string? By calculating percentage string efficiency. By calculating percentage string efficiency. What for this one? It is a measure of utilization of insulators in a string. And what is the formula? You have voltage across the string divided by N into the voltage across insulator near power conductor total multiplied with 100. This percentage string efficiency. And you also have this data further. Regarding the number of strings required for a given operating voltage and what is the ground clearance. So for a given operating voltage and the ground clearance, we can check. Ground clearance means the height of the conductor from the ground level, the number of insulators. So we check from 66 kV, 132, 220, 400. For 66, what you write? 5. Sorry, for ground clearance, of 20 meters, 26, 30, 35 meters. Number of insulators required are 5, 8, 13 and 22. So these are the number of insulators required. And suppose this third disc is damaged. In case of damage, the disc must be replaced with the identical disc. And disc is a disc, the string makes, as the string is flexibly connected, it will make horizontal oscillations and it can suppress wind effect. So in case of a disc is damaged, replace only the damaged disc. So in case of damage to a disc, so what you do? Replace the damaged disc only, not the total string. Next one is, as the string is flexibly connected, it makes horizontal oscillations and at the same time suppresses the wind effect. At the same time suppresses wind effect. So this is regarding string or suspension insulators. Now we come across the distribution of potential across the string of insulator. Now please observe, though each insulator is designed to withstand an operating voltage of 11 kV, the distribution of potential across string of insulators is not uniform. The distribution of potential across string of insulators is not uniform. The insulator near power conductors operates at more than 11 kV. The insulator near cross arm operates at less than 11 kV. So this is regarding the string or suspension insulators, and further we continue the non-uniform distribution of potential across string of insulators after this 5 minutes break. Okay, first question is by Nidhi from Kanpur. In question number 18, single phase to neutral capacitance equals total capacitance. Now, neutral means you write 2 pi please. Only that formula we use and calculate. And it is total capacitance as we have stated. Next question is by Sirisha. Why silica is not most preferred compared to porcelain? Only due to cost, please. Next question is by Sirisha. What is ground clearance? Now, the height of the conductors from ground. You name it as ground clearance. Next question is by Shailesh from Bikaner. Two-phase system is not practically used. Why? There is not any existence of such system? No, two-phase system we never use, please. Due to drastic changes, we made from single phase to three-phase. But in two-phase, due to the disadvantage of the 90 degrees phase shift, not 180. It is 90 degrees phase shift. We are not using two-phase. And is there any specific reason to use the insulators of like chocolate color? No, that composition of 20% silica, 30% feldspar, 50% clay will give you that chocolate color. So now we check the non-uniform distribution of potential across the string of insulators. Across the string of insulators. So earlier we have represented an insulator. How two insulators are connected? By means of metal part. Again, second, third insulators are connected by metal part. So between two metal parts, what you have? Dielectric. So two conducting surfaces separated by dielectric, we get capacitor. So an insulator is electrically represented using capacitor. An insulator is electrically represented using capacitor. So you consider 4 insulators. So each insulator represented with capacitance here. And here you represent the tower structure. And what about this one? Here you have cross arm. And you know any two insulators are connected by cross arm or by means of metal part here. Any two insulators are connected by metal part. Now tower made of metal, here also metal. So in between what you will get? One more capacitance, because we have a metal part, here tower made of metal. Between two metal structures, what we have? Atmospheric air acting as dielectric. So you get one more capacitance, you name it as earth capacitance C. What about this one? The self-capacitance of insulator is MC. The self-capacitance of insulator is MC. So you indicate the tower structure, cross arm, any two insulators connected by metal part. So between two metal parts or two conductors we have dielectric, that is equivalent to a capacitor. So electrically an insulator is represented using capacitor. Now tower made of metal, here metal part, in between atmospheric air acts as dielectric. So you get another capacitor. So further analysis we continue after the break.